Welcome to our session. I am Jerome Chang. I am a Silicon architect with Azure Edge Device Platform and Services. And today you will learn about the latest co-development efforts between Microsoft and ARM, partnering to build a toolchain, deploying machine learning model from the cloud to the edge. In this short presentation, you will get an understanding of how Azure Percept forever changed the accessibility of edge-based machine learning since its launch in March this year, and how ARM will make it possible to emulate the performance of your system before it's even deployed, at scale and securely through Azure. What problems are we actually addressing? Well, traditional development that did not involve machine learning deployment would typically follow a one-time and done development and deployment cycle, leaving operators to hope for rare necessary updates as they would imply minor intervention. Sounds familiar? Now, fast forward to 2021. When deploying to ML inferencing capable devices, the idea of a one-time trained and deployed model is extremely optimistic, given the limited testing that could be done before deployment and the inevitable need to optimize each node with the curated training set it requires for its best inferencing performance. This is what Azure Percept and ARM fixed virtual platform were destined to change. We'll tell you all about it today. Our joint efforts are building on what we announced last year at ARM Dev Summit. We did set the stage for an intelligent edge software development toolchain, delivering a unified and streamlined AI experience for developers. Before we put pen to paper, wrote a single spec, designed a single piece of hardware, or wrote a single line of code, we took the time to listen and learn, and we spoke to many of you. All these discussions and meetings resulted in us hearing these 8 top issues. What was the biggest takeaway? Well, how consistent these issues are for organizations, no matter the industry, no matter the location. We heard these issues over and over again. From what we have learned, Azure Percept was set to become a seamless silicon to service solution based on 3 pillars: a hardware reference design and dev kit with AI capabilities, an integrated edge AI platform with machine learning lifecycle management, a vibrant partner ecosystem for independent software vendors to thrive. Because there is no one-size-fits-all, because there is no winner-take-all at the edge, we are working on different form factors of edge appliances, ranging from infrastructure to end nodes, from server-class Neoverse cores down to Cortex-M microcontroller through Cortex-A series of processors. The ability to code once and deploy anywhere is at the center of our collaboration with ARM. Real-life example proliferated since our launch in March, helping non-ML or hardware experts to focus on their applications, not the code, even less its acceleration. Here are few implementations paving the way to autonomous behavior at the edge. From building automation to manufacturing, examples kept pouring as Azure Percept removed the complexity of learning a new toolchain. What made it all possible? It is the ability to continuously integrate and deploy our Azure Percept workloads on ARM cores. We bridged the gap between iterative development and operations activities, 2 typical siloed activities, by enabling automation in building, testing, and deploying AI applications to ARM IPs. A cloud-native development environment enables regular over-the-air updates. It provides the flexibility needed for data scientists to independently update their models. It addresses the security concerns throughout with model encryption at rest and in transport. This co-development is building on ARM projects Cassini and Centauri, creating a secure foundation for a cloud-native experience at the edge. This is achieved through a standard-based approach to platform and security with hardware underpinned by ARM system-ready programs. In a nutshell, Azure Percept Toolchain on ARM delivers an integrated device lifecycle management experience, a seamless, continuous integration and deployment mechanism to securely transport your models and data across the broad portfolio of ARM ecosystem devices. So what's next? And what's hard with hardware? Well, when building your journey at the edge, procuring hardware for large-scale testing may quickly become a bottleneck for developers, especially in 2021. Beyond the cost aspect of maintaining board farms for testing and validation of your models, these boards are simply not available in the cloud. This is when ARM Fixed Virtual Platform kicks in. The general idea about a virtual platform is that they can be useful not only for ARM licensees to validate their designs, but also, and more importantly, to all Azure cloud users seeking for a way to quickly test the performance of their applications. We highlight two cases here. The first one is a concurrent testing across multiple virtual targets, which allows for faster ML performance convergence. And the second, further down your integration path, using virtual hardware allows for testing of your application before its actual deployment. You will find a dedicated session hosted by Stefano Cadario. It's called Enabling Cloud-Based Software Development for the IoT Long Tail to dig in further. And you will learn how to optimize and profile for cores before they are publicly available. You will get an accurate measurement of system-level issues since caching and memory accesses have such a huge impact on ML execution. You will see how it fits in continuous integration plans so that we don't always have to test on external hardware.
Hi everyone, this is Gopal Raghavan. I'm a software architect in Azure Edge devices. In this portion of the talk, we want to describe some work that we are doing jointly with ARM on emulating Azure Percept devices in the cloud before you actually deploy it. Or alternatively, you could call these as virtual targets, which we would like to deploy in software and debug the entire process before you use any hardware. We'll begin by describing our Azure Percept MLOps tooling and then explain how emulation helps various portions of your MLOps pipeline. The Azure Percept family of devices has three main value propositions. The first one is security. The second one is ML lifecycle management or MLOps. And the third one is device lifecycle management. Edge devices typically tend to interface with the physical world. And as we know, the physical world is always changing, which means your model performance will change over time. So you need to be monitoring performance, and you need to have a CI/CD pipeline that's updating your model and deploying it to the device when the performance is not satisfactory. And finally, you have device lifecycle management, which is how you deploy tens of thousands, million devices. How do you monitor them? How do you upgrade software, even the ML model? And finally, retire these devices at end of life. To accomplish all these goals, we tend to use a variety of devices and models to meet both energy and performance targets. So on one side, you could have really small devices which live off a tiny solar cell for energy harvested applications, but you can only deploy smaller models on these devices, and so your performance is limited. The other extreme is the cloud, where theoretically you have infinite performance, and anything in between. You could deploy on the gateway if you want, which is better than the edge but weaker than the cloud, and so on. And you could use a variety of power sources for the edge. For example, it could be energy harvested with really tiny devices. It could be battery operated for a medium class of devices. And finally, it could be wall powered when you have larger devices. Now, when you're building your system and you're not sure which device you want to use to meet your performance and energy requirements, it doesn't make sense for you to buy the hardware, try it out, and find out that it doesn't meet your requirements. And this is where the work we are doing with ARM on emulation in the cloud is key, because you can verify that whatever device you pick and the model you use is able to meet your energy and performance targets before you actually make any hardware investments or hardware deployments. Let's get into a bit more on the virtual hardware emulation. I would urge you to look at Stefano's talk on enabling the cloud-based software infrastructure for long-tail IoT. He discusses this in a lot more details, but as far as our needs go, the main things to remember here is the ARM virtual hardware platform is hardware accurate and it is really fast. This allows us to not only emulate the hardware but the whole software stack all the way up to business insights. So we can emulate the deployment process, including digital twins. We could emulate the complete data pipeline from sensors all the way to business insights. You can connect it to IoT hub and actually receive data from the virtual target. And what this allows you to do is a variety of partner silicon can be emulated, and you could determine what's the right hardware choice for you to achieve your goals for performance and or energy. In this slide, I want to go over a simplified version of our Percept MLOps pipeline. And let me walk you through this. We should get my laser pointer here. So this is a data lake, the Azure data lake, where you have raw data. So in the beginning, you save your training data, everything into the data lake, and then you use our AML platform to train a model. Amongst other things you can do to optimize your model is to run neural architecture searches or choose a standard model, also do feature engineering, hyperparameter tuning, and even model compression in order to get the best model you think you want. Now at this point you have a model and you want to figure out which device should it be deployed on. And so what you do is, this is the inner loop, is a software emulation loop, and we'll get into this a bit more detailed. And then what happens is you deploy it on IoT Hub, and here we can deploy it as either a virtual device or a physical device. And the virtual device will send data to IoT Hub, and this would go to all your business insights or any other alarms you want to set. So this is the whole Azure Monitor platform, which I won't go into, but I urge you to do a quick search on it, and we have a lot of documentation on this. There are so many applications that you can look at. And what we also do is these devices, once in a way, will send raw data that gets added on to your Azure data lake. And as I said, this whole process is a CI/CD process. So new data comes in, the model gets trained, and you look at your performance. If the performance is good, there's no reason to do anything. If your performance is not good, you would again go through, and this time you would not choose a device because your device is already chosen and deployed, but it would go through and a new model would get deployed to the physical devices. So this is our overall Percept MLOps chain, and I'll go into this a bit more detail in the next slide. The first step is you want to optimize your model for your edge devices. And what you start off with is you start off with your training data and validation data, run it on the cloud, on your machine learning platform. Here, of course, we would use Azure Machine Learning, and optimize your model to satisfy primarily your energy and performance requirements, which means you have some estimate of how much memory you need, how many cycles you want, and so on. And that would be step one. In step two, you would take the model you got and you would choose your device. So let's say you choose an M7 device or an M55 device, and you would convert the model, and this would be all automatically done for you. Here I'm just pointing out that you'd have a choice of different models and different vendors, and the model would be converted and then deployed on a virtual target, which is a Corstone 300. And the output of this, you check whether you met your targets or you didn't meet your targets. Now, if you didn't meet your targets, presumably you could choose a different device with more memory or multiple cores or an AI accelerator, whatever. And you go through this inner loop to see if you can meet all your requirements. Now, it's possible that the library of devices you have is not able to get you where you want to be, in which case you'd have to go through this loop again and develop a new model, or take this model and further optimize it to meet your requirements. So at the end of this step, you've chosen your device and you're convinced that, or you're satisfied with the model and the performance on that particular device. In this slide, I just repeated what I said before. You may have to go back to your model and your data and retrain the model because you are not able to meet your performance requirements using the devices in your library. So you go back to your model. Okay, we are almost there. You've chosen a device and you've chosen a model that meet your requirements. And now you deploy these in a container in the cloud. And then you also deploy your whole software stack that connects your device to the cloud, in this case, Azure IoT Hub. And you can start debugging the data pipeline, which goes from IoT Hub to either the business insight side, which is this pipe, or you can go and debug data that comes and gets raw data from the sensor that goes back and gets put into data lake, which you can use to retrain your model. So you're debugging this pipeline and that pipeline going to the cloud using your virtual targets. So finally, you're at a point where you can actually do a physical deployment. You know what your device is. You've simulated it. You know what your model is. You know the performance is satisfactory. You've set up your whole pipeline. And at this point, you swap your virtual device with a physical device. The physical device will now send data through IoT Hub, and it should be seamless. The good point about it is you have not spent your time and energy trying to get a physical device, many physical devices, play around with all of them to see which one meets your requirements. And the reason this works so well is because of two benefits that the Corstone models bring you. One is the accuracy. These are vendor models and they are accurate. Vendors use these to build their chips, so you can be guaranteed that there won't be any performance differences between this model and the physical device. Number two, the speed of virtual emulation allows you actually to run the full software stack on your virtual device so that it connects to the cloud and you can debug any issues you have with your software stack running on the device.
Before we finish this presentation, we wanted to give you a quick demo tour. Thanks for watching.
This is the directory structure where container is the one toolchain provider will own this directory, where they have a Docker file, they have a pipeline file, and this file is being used by this Docker file. Likewise, Cortex-M container will be owned by a toolchain provider. All the files needed for building the container and pipeline right here. Then a script for one candidate model, which we have selected, is here. So this is where you can find all source code. And these are some extra, some PNGs we have, some other stuff like images or other stuff we keep here. So this is how the hierarchy looks like for a repository. So total we have, I believe, 8 pipelines. One pipeline, the first pipeline to set up resources on Azure. So that is that creates IoT Hub, storage account, Azure Container Registry, Azure Container Registry at the 3 resources. And then we have two, one for Apache TVM Toolchain container, Cortex-A, and same way for Cortex-M, we have this container pipeline. And other than that, we have developer pipelines. We have 3 developer pipelines so far for Cortex-A, and we have 2 developer pipelines for Cortex-M. One, it uses the same model, but different devices it targets. One targets STM32, another is SparkFun Edge. So we can see here, it acquires the model. Let me open up code as well. This is how our inferencing app looks like. It is using the IR files, all the 3 files, and then it will take input of our kite image, and it will do the object detection with the help of this model, and finally it will output a file, a PNG file. All right, so I'll go to the pipeline. Also, it executed successfully. Download a step, successful. It also converted, exported all the 3 files. We talked about these 2 and this on 3. And then this is where, Vishal, you can see here, all the steps are seconds, you know. Now let's go back to our device on IoT Hub. We can see the new module, test container YOLO. It was deployed like, you know, half an hour before today. So I'll go to the device now. Okay, so since this model is outputting a file, I have created a volume so that we can see visually. Otherwise, seeing in a command line would be not that interesting. Meanwhile, let's keep an eye here. So our container is created because we can see here the test image is here. Looks like container ran. So one more image will come, the output image. Yeah, so output image came. Here is the cat. We boxed her. So yeah, so it's working fine. I can see on the device as well. This is object detection model. So this was our input image, and this is our output image.
Now it's time for some call to action. Please go to the website listed here, get your Azure Percept dev kit, and check out how easy it is to deploy models on it and connect it to the cloud. We also encourage you to go to Azure Machine Learning with your own data and optimize your model and see how efficient and how easy that is. And finally, use IoT Hub to emulate and deploy your models. And let us know if you have any issues or questions. We'd be happy to work with you to get you to use Percept devices. Thank you very much for your time, and we hope to work with you in the future.